So today is going to be the final interactive video for these lesson tests. We're on the last one, and it's going to be on the cross product. This is probably the most in-depth lesson task we have so far, and for good reasons. So we talked about the dot product. The dot product is very nice, and it computes a scalar that tells us how the directions are close to each other for two vectors with the same position location. And again, position doesn't matter, so you can always have the same exact initial position. It's just the terminal position might not be the same, and the direction as well, and the length and all that stuff. So, before we get to 9.5, we need to introduce a few things. The cross product is symbolized with that X. So if you did on definitions, I had to take off points, unfortunately. But let's work with this. Let's suppose I have a matrix. You should have worked with matrices in pre-cal algebra. But let's say I have a 2 by 2 matrix, 2 rows, 2 columns, right? All of the numbers inside this matrix or this box are numbers. A, B, and C, D represent numbers. So before we can talk about the cross product, we need to talk about the determinant of a matrix. This is going to be relating to matrices. However, we need a tool for vectors, and that's the cross product. But we have to talk about how the determinant affects a matrix. If I wanted to find the determinant of A, I can compute this, it's not absolute value, by calculating A times D minus B times C. This is very nice. I can work with a 2 by 2 very easily with this, and I get a scalar out of that. Determinants are scalars. However, cross products are not. So I can calculate the determinant of a matrix, multiply those corners, those diagonals, and then subtract them from one another. I get 10 in this case for this example. Then the question is, what happens in a 3 by 3? Because with a 3 by 3, I have more numbers to work with, and it might not be as simple. So mathematicians, what they do instead is they turn the 3 by 3 into 2 by 2s. So they can work with that definition. So how do I turn this to a 2 by 2? Let's say I have these set of numbers in my matrix. My goal is to break this into a 2 by 2 matrix. I can have multiple matrices, but if I can break them down 2 by 2s, I can work with them. So we do something called a cofactor expansion along the first row. The cofactor expansion along the first row, what that states is that we're going to use the first row and create matrices where our first entry, or the entries in our first row, will represent the scalar times whatever is remaining for our matrix. What do I mean by that? So there's some text here so you can read that to get more idea, but we're going to eliminate all of the entries on the same row and column of the entry we choose on the first row. So for example, the first entry on the first row is A sub 1. I'm going to eliminate all of the rows and columns for or where A sub 1 lives. And if I do that, I have a 2 by 2 matrix left. B1, B3, C2, C3. So I can write it multiplied by a scalar times A1. And I can calculate a determinant of a 2 by 2 now. Determinant of that is simply A1 times B2, C3 minus B3, C2. These are all general terms to get you the idea and generalize things for different matrices, but they have the same rhythm. Now I need to calculate the second cofactor expansion on the second entry on the first row, A sub 2. So I do the exact same procedure. I look where A2 is at, and I'm going to eliminate everything on the column and rows. Doing so, I do get a scalar, A2, times the determinant of a 2 by 2. Boom. And this was created because we needed an operation that was similar to multiplication. And then I'm going to do it for the final entry on that first row, A sub 3. If I do so, I have this ending term here. So that's great. If I put them all together, I have this term over here. Now, I have positive A sub 1 minus A sub 2 and positive A sub 3. I alternate the signs for reasons. I do alternate them. I go from positive, negative, positive, negative. And I'll explain why in a bit. But if I decide to expand it out, I have these set of terms. Okay? That is how you do the cofactor expansion to calculate a determinant of a matrix. And there's a little example here. You guys can look at this in your notes and whatnot. This is the prerequisites. Calculating the determinant where I use actual numbers. So see if you can do that. Just worry about getting the cofactor expansion. Don't worry about calculating the full determinants. Just get the expansion for each entry in the first row. Boom. And then if you want to verify by alternating the signs, you should get negative 38 for that problem. All right, so that's the prerequisites. Now let's go to the actual thing you need to learn for lesson task. All right, that is a prerequisite. Now we're going to talk about the cross product. The cross products relate two vectors. This idea of multiplying vectors, we don't have a good definition of it. There was a guy named Hamilton who wanted a good definition, but he couldn't work with it initially. He realized that, hey, to actually work with multiplication among vectors, I have to introduce a fourth dimension into my problem. I can't just work with these two three-dimensional vectors. I have to do something else. So this idea of the cross product is going to tell us that the cross product between v and w is going to show an orthogonal vector w that it will be orthogonal to v and u. That means their dot product with u and w should be 0, and a dot product between v and w should be 0 as well. So it needs to satisfy both conditions. So how do you do this? Well, I'm going to expand the dot product for u and w and v and w and set it equal to 0, because that's what we need. And then the u is split into, or the components of u are a sub 1, a sub 2, a sub 3. The components of v are b sub 1, b sub 2, b sub 3. And w is what I want. There's c1, c2, c3. Those are the variables. If you look at pre-calculus algebra, this is just a matrix, an augmented matrix. So I can solve this by reduced row echelon form. I'm not going to require you guys to do that, but I just want to show you that this is what my solution should look like. A vector w, where I have these as my components. A sub 2, b sub 3 minus a sub 3, b sub 2. That's the first component, and etc. You can see all the other ones. Well, I need to construct the cross product in a way where I get that solution. So we say the cross product between u and v, u cross v, is going to have some sort of determinant where I get that solution. But the problem is, how can I get a vector out of the cross product when the determinant was always a scalar? So what we're going to do, and plus I have two vectors, two three-dimensional vectors, that creates a 2 by 3 matrix. So I have two issues I need to tackle. Well, to fix that 2 by 3, I can add another row that turns it into a 3 by 3. And to get a vector out of it, instead of using scalars or real numbers for the first row, I can just use vectors. And I'm going to use the third vector, I, j, and k. Well, so that's three vectors I'm going to use, but they're all going to be in the first row. So I have a 3 by 3, but that first row is going to be all vectors instead of real numbers. So here's what it should look like. The example I'm going to give you is some concrete u and v values. If I want to do the cross product of u and v, I'm getting the determinant of this array where the second and third row are just u and v, where the components are for I, j, and k. The I component for u is 1. The I component for v is 4. The j component for u is 2. The j component for v is 5. I keep doing that process. And to turn it into a 3 by 3, because I need that box, I don't want a rectangle, I introduce that first row I, j, and k as vectors. Okay? And then doing the determinant should get me a vector. So if I calculate this out right here, did the cofactor expansion, I get this right here. I get the 2 by 2 determinants all multiplied, not a scalar, or the determinants are scalars, but is being multiplied by a vector I, j, and k. Those are vectors I, j, and k. This means if I calculate it all, it should be a vector. Then the question is, why do we alternate plus or minus signs? Well, that's actually a very easy question to answer. So w, if I solved that matrix a while back would reduce row echelon form, I get that the solution should be in green. However, that doesn't match what the determinant says. So what I need to do is, if you notice, that second component is literally the same as my second determinant component, just that it's flipped, or the signs have changed and I commute the two terms. I swapped a3 and b1 with a1 and b3 and had the negative swap for that. So I have to introduce -1. I factor out a -1 in that case. Everything else is positive. So the idea is that it's going to keep alternating. So if there was 4 terms, it would be plus, minus, plus, minus. And that's because we want it to be the solution for my system. So let's do an example. Let's say I have u and v here, and we want to calculate that. We want to calculate the cross product of the two vectors. I want to find that third vector, u cross v, that is both orthogonal to u and v. So I construct my determinants where the first row is the ij and k vectors, and then the second row will be the row u, and the third row will be the vector v. All right, you can correspond each of the ij component if you would like to. All right, and then I have my cofactor expansion. That's nice. And then I can put this all together. When you get better at this, you'll put them all together at once. But for now, I recommend you split them up just so you have more practice. Once I put them together, I have alternate the signs. I have plus, minus, plus. And then I have my u cross v as this vector, -2 times the vector I, 6 times the vector j, 2 times the vector k. Now I calculated the determinant, but please show your work in that just in case. The notes was getting a bit too long, so I wanted to clear that up, and hopefully you guys practice that just to verify if it's true or not. So that's the vector u cross v that should be orthogonal to both u and orthogonal to the vector v. Good. So what does it tell us? Well, u cross v is orthogonal to both of them. That means the dot product between u cross v and v should be 0. Likewise, the dot product between u cross v and the vector u should also be 0, the 0 scalar. Remember, dot product outputs a scalar. The cross product outputs a vector. So, now, if that vector is the 0 vector, not the 0 scalar, if it is the 0 vector, so 0i plus 0j plus 0k, which is giving me the 0 vector, then we can say u and v are parallel. That means there's no orthogonality, or there's no orthogonal vector that satisfies being orthogonal to both u and v. All right, this is the kind of the other idea we have with the dot product. The dot product says if I equal 0 scalar, they are going to be orthogonal. Whereas the cross product says if I get the 0 vector, they are going to be parallel. So there is some, I guess, nuances you have to be careful about. Now, if you're taking physics and everything, we have something called the right-hand thumb rule. This is a very powerful rule when working with 3 dimensions or even higher per se. So what does that third vector that's orthogonal to u and v look like? How do I know which way it goes, which direction, or anything like that? It can be very confusing because u and v might have all 3 components x1 or x, y, and z. So how do I know where that orthogonal component lives? How do I know what it looks like? How do I draw it? Well, we have the right-hand thumb rule. And what it states is that you're going to stick out your right hand, and then the curl of your finger will be the direction of the angle. So make sure you match up the curl with the direction of the angle. In particular, the first image right here, if I keep rotating that curl, it'll be in the same direction as theta. Then wherever your thumb is, that's going to be the direction of your orthogonal vector. In this case, it goes straight up. Now, this is kind of clear in this case for this first image, but remember, sometimes we might have a vector sideways or whatever. We're working in 3-dimensional space now. It could be upside down or anything. So I need to know where that orthogonal vector lives if I have 2 random vectors. So I give another example of what happens if it's sideways. Notice that the curl of my finger is pointing, or the curl of this image right here, is pointing towards the direction of theta. I want it to match. Once I have it matching, this is my right hand still, my thumb will point to where that orthogonality lies, where u cross v will live. And in this case, it's this image right there. So this will help you orient yourself for physical applications. So now that we know that it's the orthogonal vector, we need to talk about the magnitude of that orthogonal vector. Well, we can actually prove that it's equal to the magnitude of u, the magnitude of v, times sine theta. I encourage you guys to look at the proof because we don't have enough time for that, unfortunately. But it's a very clear proof and is a very elegant one as well. It involves using the definitions and dot product. There is a bit of algebra you have to manipulate. All right. So this magnitude idea is exactly the magnitude of the cross product is the magnitude of u, the magnitude of v, times sine theta. Okay, this is kind of familiar, but the sine theta is kind of throwing some of us off. So what does this tell us? Well, let's look at an area of a parallelogram before we even talk about it. Area of a parallelogram, how do we calculate that? That's similar to a rectangle. However, I need the height rather than the side lengths because the side lengths are slanted. So I get my base, the base length, times the height. If I do that, I will get the area of the parallelogram. Well, notice that to solve for h is just, well, the magnitude of v times sine theta. And how is it that? Well, notice that the angle opposite, or the side opposite from theta, is the one we want h. Well, it's opposite, and I have the hypotenuse of that triangle, right triangle I drew. So I can multiply the magnitude of v to both sides, and then I get h is equal to the magnitude of v times sine theta. All right, so that's cool. That means I can rewrite the area of a parallelogram as the magnitude of u times the magnitude of v times sine theta. But wait, that's exactly the magnitude of u cross v, which means they're exactly the same. So doing the magnitude of the cross product will give me that area of that parallelogram constructed by the vectors v and u. So that's a very powerful thing. And if you wanted to calculate the area of a triangle, similar to a rectangle, I can break it up into two triangles. That means the area of a triangle is simply the magnitude of the cross product u and v, that parallelogram, divided by 2. That is it. All right. Now, we are working in 3D, so we need 3D figures. That was just a two-dimensional case. What happens if I wanted to calculate the three-dimensional figure of a parallelogram? You know, it has the same properties as, or I would call it a parallelogram prism, but the formal word is parallelepiped. So the parallelepiped is a three-dimensional parallelogram that's extended with its height from the base of the parallelogram itself. And when I say base, I don't just mean a one-dimensional line. I mean a two-dimensional area. So we calculate it similar to how we do with any prisms. You calculate the area of the base times the height. Similar to cylinders. Cylinders can be seen as prisms as well. You calculate the area of a circle, and then you multiply by the height. Same with rectangular prisms. All right? So we introduced something called the scalar triple product. Since the volume has to be a scalar and not a vector, we need a scalar out of our cross product somehow. So let's say we have the scalar triple product of the vectors u, v, and w. All right? That means I need the cross product v cross w dotted with the vector u. So let's have these notation. U has the a components, v has the b terms, and then w has the c terms. Now, normally when I did the determinant, or when I did the cross product, that first row are all vectors, and that's how I get a vector out of it. That's how I get a vector out of that determinant or cross product. All right? But now I'm going to change it up. I have 3 vectors already, so I can have a 3 by 3. Clearly, I can have a 3 by 3 if I just align them correctly. And moreover, the entries of each vector are real numbers. They're not vectors. U, v, and w are vectors, but their components are real numbers. So I can just write out that first row being the a component instead of I, j, and k. This ensures that I have all scalars. So that means if I calculate that determinant, it is a scalar. And the dot product is a scalar, so this definition does still hold. So I do the exact same process, but with scalars this time. And notice that negative that we alternate with, that is not on the scalars. That is on the determinant values. So a lot of books will write the negative on the scalars, which you can do that because it commutes, but it's more clear to write the negative on the determinant of B1, B3, C1, C3 times the scalar A2. They'll still be the same thing, but this is more clear in my opinion. All right? And this is, if you think about it, this is actually just a dot product. I'm getting the components of U multiplied by the determinant of the vector of B and C, which is exactly the dot product, or multiplying the components out. So the definition still holds for a dot product. So this is me talking about prisms and whatnot. I think that's a very helpful thing that you learned in high school. Some of you guys might not have, so it's not that big of a deal, but I will use that information to calculate the volume of a parallel pipette. So the volume of the parallel pipette can be denoted as U dot the cross product of V and W. Well, why does that work? Well, let's look at this. If I draw my parallel pipette right here, the area of that base, I told you it was the magnitude of V cross W. The magnitude, or the magnitude of your vectors cross the other vector that forms that parallelogram. In this case, it's V and W, not U and V. All right? Now, because it's a prism, I'm going to multiply it by the height, and that is exactly the volume. Well, I need to calculate that height. I know that 90-degree angle, which gives me height, is the vector V cross W. That's the vector orthogonal to the vectors V and to the vectors W. So that's nice. It is orthogonal. Well, I don't want the entire length though, so I draw a triangle to construct this. And if we notice, we follow that same idea, but instead, I want to calculate the height, that's the adjacent part of the triangle in relationship to theta. So I got cosine theta equals height divided by the magnitude of U, which is equal to the height is the magnitude of U times cosine theta, which this forms that proper, or the volume itself. So I can rewrite the volume of the parallel pipette as the magnitude of V cross W times the magnitude of U times the absolute value of cosine theta. Cosine theta is a scalar at the end of the day. I do the absolute value because cosine can be negative if you're past pi halves. So we need the positive value because you can't have negative volume. All right? Well, this is just the definition of the dot product. I have two magnitudes multiplied by each other times cosine of the angle. That is literally the definition of a dot product. If you don't remember, U dotted with V is equal to the magnitude of U times the magnitude of V times cosine of theta, which if my other vector instead of V is V cross W, this is the equivalent definition. It's just that cosine has to be positive. All right? So that's nice. I'm able to show you that the volume is exactly the triple scalar product. Well, another thing we need to know is that, hey, what happens if my volume is 0 for that parallel pipette? Well, that means they all lie on the same plane because there is no volume. There is no height in that particular case. So they must be coplanar. They lie all on the same plane if the volume is 0, the scalar 0. So an example here is show U, V, and W are coplanar. The idea is that I'm going to compute the triple scalar product. And as long as the triple scalar product is 0, the dot product between U and V cross W is 0. And if I'm checking if it's 0, it doesn't matter if it's positive or negative. So I took away the absolute value. It doesn't really matter. All right? And it's the absolute value and not magnitude because it's a real number. It's a scalar. So then I do the exact same property. I look at my first row, get the cofactor expansion, alternate the signs, plus, negative. In your book, I think they use -1 raised to the ij power times mij, but we're not going to talk about that. That's for matrices. But then I get a scalar of 0 at the end of the day. Be careful with your signs. So the volume of the parallel pipette is 0. Then you can say U, V, and W, the vectors, are all coplanar with one, or they are coplanar. They live all on the same plane. And this is a very powerful thing that we can do. So that's pretty much it for the cross product. Be sure you take notes on that. I'm assuming there's no questions on this because I have yet to see any student in office hours. But if you guys are still confused with this, feel free to come to my office hours, ask any questions if you like to. I would love to clear any confusion on this. And that is the last interactive video for this semester. So take care. Bye.